Day 14. We've got about 50 people on the leaderboard who have done all of the days up until now. So they've got 26 stars total, part 1, part 2 every day. We've got a few more who look like they have just maybe not gotten to yesterday's problem yet. And checking the local score for the speed demons, we've got a new third place. We've of course got Talk Lyman first, as usual, and anonymous user. But in third place today, we've got Sergey, edging out the previous third places, Frobiak, Joshua, and Bully. That's pretty fun. It's pretty fun to see third place changing every day. Let's get over to the calendar. We've got about another 60 to 90 seconds before day 14 gets started. And okay, here we go. What do we got? The distress signal leads you to a giant waterfall. Actually, hang on, the signal seems like it's coming from behind the waterfall, or from the waterfall itself, I guess. That doesn't make any sense. Path leads behind the waterfall. Distress signal leads us to behind the waterfall. It's a large cave system. Feel the ground rumble. Sand begins pouring into the cave. If we don't quickly figure it out, the sand's going to get us. Starting to sound like an Indiana Jones movie. This is a link to 2018, day 17. You scan a two-dimensional vertical slice of the cave above you, which is the puzzle input, and you discover that it's mostly air with structures made of rock. So puzzle input, I think, looks like this. Or maybe it looks like this. This might be our puzzle input. Scan traces the path of each solid rock structure and reports the XY coordinates, where X represents the distance to the right and Y represents the distance down. Each path appears as a single line of text in your scan. After the first point of each path, each point indicates the end of a straight horizontal or vertical line to be drawn from the previous point. Okay. Scan means that there are two paths of rock. First path consists of two straight lines because the numbers match. Okay, got it. And the second path consists of three straight lines. Are they all straight lines? Sand is pouring into the cave from 500 0. Looks like a hard-coded number. Drawing rock is hash and air is dot. The source of the sand is plus, and this becomes this. Okay, so there's some rocks and some air. The sand is filling in here. Sand is produced one unit at a time, and the next unit of sand is not produced until the previous unit of sand comes to rest. A unit of sand is large enough to fill one tile. A unit of sand always falls down one step if possible. If the tile immediately below is blocked by rock or sand, the unit of sand instead attempts to move diagonally one step down to the left. If that tile is blocked, the unit of sand attempts to move diagonally one step down and to the right. Sand keeps moving as long as it is able to do so. At each step, trying to move down, then down left, then down right. If all three possible destinations are blocked, the unit of sand comes to rest and no longer moves. At which point the next unit of sand is created back at the source. So drawing sand that has come to rest at 0. First unit of sand falls down and stops. Then falls down, goes to the right, falls down, goes to the left, to the right, to the bunch of them. Okay. Once all 24 units of sand shown above come to rest, all further sand flows out the bottom, falling into the endless void. Just for fun, the path any new sand takes before falling forever is shown here with tilde. Okay. Using your scan, simulate the falling sand. How many units of sand come to rest before the sand starts flowing into the abyss below? Okay. Probably just a B-tree map, right? We draw all the lines, we put all the rocks in. We start sand off at 500 0, I guess, or 500, whatever that is. We have to keep around these IDs, I guess. And then we can just calculate the sand. So each iteration, we have one piece of sand that we're controlling, and we just run that piece of sand until it's supposed to stop, and then we insert it. And then we do it again, and again, and again. And then at the end, our stop condition is we should probably find the lowest rock. And if the sand starts falling below the lowest rock, then we know we're done. So here's our input, our test input anyway. Let's check our puzzle input. Puzzle input is very similar. I think that they're all either vertical or horizontal. There's a lot of points. I think we can just insert all of them. There's probably some optimizations we can do, but I think I'm just going to insert all of them to start with. I think that we can do ranges to do that. So the input is this, and the answer is 22, 24. So 24, ignore the second test. We're going to start off with a line parser because the regular parser is just going to be a separated list of lines. So one thing that I do want to mention, somebody ran into an issue where they were using their test input in a separate file on Windows and it wasn't working for them. So instead of doing a separated list 1 with a new line, we can do a separated list 1 with a line ending. And that'll account for the new lines that you would find on Windows, as well as the new lines you would find on Unix or Mac systems. So the difference there is either carriage return, line feed, or just the line feed. So we have to import these, do that through Rust, or do that through Rust Analyzer. Right now, this would be a vec of unit. I'm using unit right now because I don't know what I want to return from this line yet. I think we're going to do a Windows over it. So we can do let input pairs equal separated list one. So we're going to look for tag space arrow space as our separator. And then we're going to have a tuple, no, a separated pair, right? Separated pair is the right thing here. Yeah, separated pair is the right thing here. So we're going to do U32, complete U32, car, comma, complete U32. I must have messed up my indent or my parentheses or something here. Separated list, separated pair. Let's get tag in here. Let's get separated pair in here. And then we need, is it complete car? I think it is complete car. So we've got a U32, a car, and then a U32. And this should give us the list of pairs. Let's debug that out, I guess. Then if we apply rocks, we get result back. And then we just need to run our tests. So we got 498.4, 498.6, 496.6. So that works for us. Then we need to do pairs.windows2.iter, right? No, is this already an iterator? I think this is already an iterator. .map AB, and we'll get this to be ranges, I think. My only question is what happens if these go lower? I think we can handle that. I think it doesn't matter what order we do the drawing in, but if we create a bunch of ranges, we do need to have the numbers go from low to high, basically. So if we do a little bit more destructuring here, maybe let's do AX, AY, right? And BX, BY. And then we need AX.maxBX and we need AX.min BX. We do a ... and those will be the X ranges, provided I get my parentheses right. And then we do the same thing for the Ys. So we have the X range and the Y range. And then we actually start reading our compiler output, expected slice found tuple. Okay, so we'll destructure the slice, and then we need to decide what to collect into. If we have 3 ranges, can we flat map this? Does that work? And then can that be a vec of U32 tuples? Patterns not covered. Method cannot be called on range U32 due to unsatisfied trait bounds. Right, we really don't want any of these to be references. Maybe I should have read closer. What does the error message say here? We probably shouldn't be zipping. We should probably just do our good friend Cartesian product. Let's just make this super explicit for the purposes of showing the types. So we've got AX min and AX max as these 2 values. Then we got AX min, AX max. This is going to be range inclusive. Can't forget that. I make that mistake all the time. And then we have the same thing happening here. So we'll do a copy paste and we will take the X's and make them Y's and then take the mays and make them maxes. And I'm just realizing that these would be better served as not having the A's in them, just as names for variables, because it's Xmin and Xmax. Okay, so now we have at least the ability to see what the types are. So AX.min whatever, AX.max whatever is a reference to a U32. If we dereference that, then we get the actual values, which is what we want. Windows does give us slices. So question, why do we need to cover the extra patterns? Refutable patterns in function. It can only be Windows 2. I get why that's a refutable pattern. It doesn't make me any less confused as to why I can't match on it with the knowledge that we did slice.windows. But we do have Iterators, and Iterators has tuple windows, which I don't think we even need to specify. We can just let it infer from the flat map, which is kind of exactly what I want it to do. So we end up with 1, 2, 3, 4, 5, 6 rocks. Is that the right number of rocks? 1, 2, 3, 4, 5. Are we duplicating any of these? I think we are probably duplicating 498, 498, 498, 496, 497, 498. Yeah, here we go. 498 and 6 is duplicated. That won't matter for us for the purposes of inserting it into the B tree. So I don't think we need to care about that. But it is worth noting that we are generating duplicates doing this range calculation. So the first range goes from 498.4 to 498.6, and the second one goes from 496.6 to 498.6, which should be this L up here. So question is, do we even need to collect this, or can we return this iterator from the parser? So if we do this, first of all, to return an iterator here, I'm using impl iterator with the item type that we have. This is kind of an advanced Rust tactic. So I would say that if you're not comfortable enough debugging this, then you should just collect into the B tree map inside of the line parser. Because one thing that we do have to do here to be able to return this iterator is ensure that the values that the iterator is holding are live long enough to be returned, which means that when we iterate over pairs, we have to use into iter instead of iter, because iter will return us references to pairs. Pairs is defined inside of this function and will not live if we return this iterator. So we can't return an iterator with references into pairs because pairs is going to get dropped at the end of this function. So we use into iter to take ownership of the pairs while we're iterating over it. We use tuple windows and flat map. Tuple windows gives us U32s here instead of references to U32s because we used into iter instead of iter. We do everything that we did already. Cartesian product generates a bunch of data, so we own that data. And then we can return our iterator by using impl iterator item equals our item type. Now we have more stuff to do in rocks. So input pairs here. So we can iterate over pairs and collect. So pairs here is a vec of impl iterator item U32, U32. I think we actually only need a B-tree set here. We don't need a B-tree map because we only need to know that these tuples exist when we're looking for rocks. We don't need to know whether they're filled with a rock or with sand. So we want to take ownership of the data we took back. So we have all the pairs. We want to turn that into an iterator itself and take ownership of all the iterators that we have inside of the vec. Then we'll flatten that and collect it. Now we flatten it because we know we have a bunch of iterators inside of this, and the other option would be like doing a for loop and chaining them all together. But flatten just lets us take all of the iterators that we have that we're iterating over, to flattening them all one level, which is putting them all together and then collecting them. So now we have a B-tree set. And if we debug that B-tree set, we should end up with all of the values. So 4949, 4945, 4966, and dang, would it be nice to have a better output to look at. So 494 is supposed to have a rock in 9. 495 is also supposed to have 9. And 496 has 6 and 9. 6 and 9. 498 has 4, 5, 6, and 9. 4, 5, 6, and 9. 499 has 9, 9. And then 4, 5, 6, 7, 8, 9, 4. That looks right to me. So we have a B-tree set with all of our values in it, returned from our parser. And of course, our return type here is going to be that B-tree set. So we won't need to put the type on map. We can just leave type here because collect will pick up on what we need to do here through type inference, through map, through the return type. So to recap, we've got this pretty simple like data structure here that we need to parse. It is range, or it is a grid cell separated by arrows. And then each set of lines is separated by new lines. For each line, we do a separated list separated by the arrows, and then a pair of U32, U32. That gives us these three cells as this set of pairs right here. Then we take ownership as we're iterating using into iter over these pairs. We use tuple windows to be able to destructure inside of the flat map. The flat map is going to flatten any set of iterators or set of values that we have here. So we get the min and the max for each of the X and the Y values. We set up a range from the min to the max for each of them. And then we do a Cartesian product to get the full list of all of the values from X with all of the values from Y. And this is doing this for each line. So we don't need to worry about different lines being combined together. This is doing it for each individual line. That's why we need to be doing flat map, because now we have 3 iterators over each of these tuples. So we've got 3 iterators returned from this pairs into iter tuple windows flat map. And doing the flat map gives us a single iterator for each of the lines in this line. So we end up needing to return an iterator out of line, which strictly speaking, we do not have to do. We could instead return a vec of tuples here. If you are newer to Rust, I highly encourage you to do just .collect right here and put a vec in here of U32 tuples. It will be a lot easier to manage. Oops, I accidentally left the collect there. Okay, we use the impl keyword to even allow us to return an iterator, because iterator is a trait. And if you've ever looked at the type of something that implements iterator, you might have seen something like a flat map struct, et cetera, a bunch of things stuck together, nested inside of each other, which would also be a valid return type here. So if I put unit here, we would get a type error. Not the type error I wanted to show you though. Whoops. So in any case, we return iterators from each line. So we can do a separated list using line ending, which will do Windows or Unix line endings with the line parser. This returns us a set of pairs that are a vec of the thing that is an iterator. So impl iterator item tuple of U32s. We want to take ownership of these items. So what we don't want to happen here is if we do iter, we get errors. And if we read those errors, we will see method cannot be called on flatten, slice, iter, impl iter item U32, U32. That's just for collect. So if we scroll up, we see the pairs.iter issue as well. And it's a little bit more clear. A reference to impl iterator is not an iterator, which sounds weird until you realize that a reference to an iterator is not an iterator. So what we need here is to not have this reference here, and then everything will go through. And we can get not having that reference there by taking ownership and doing into iter. All that to say, we flatten all those iterators together and collect them into a B tree set. So now here in process part 1, we have a B tree set of all of the points that have rocks. And then we loop. And our loop strategy is what? We probably need a current sand that's a tuple. I think this starts out at, let's start this out with none, actually. Let's make this an option of U30, U32, U32. This needs to be mutable. The sand is pouring into the cave from point 500, 0. So we need to take the Y value and increase it to go down. So the sand always falls down one step if possible. I wonder if we need to count steps. We're only counting 24 units of sand, so I don't know that we need to count steps. So I think current sand can just equal our tuple. So it's going to be 500, 0. And then we do sand move, basically. So we want to do current sand dot 1 plus equals 1. This is our desired first move. So let's do a generation. Let down equals current sand dot 0, comma current sand dot 1 plus 1. So this is theoretically moving it down. Then we also need the exact same thing left and the exact same thing right, except that this will be -1 and this will be +1. And we've used U32s, so I'm just kind of hoping that we never go negative. If we go negative, then we have a problem, I guess. We could probably take a look at the input. I think all of our numbers are at like 500. So worst case scenario, we fall off at like 400. So we've got the desired down position, the desired left position, and the desired right position. If let sum cell equals, and what do we call this? We'll call this board. Board dot get down. We have a valid down move. We should move the piece of sand down. So current sand equals down, if we can move it there, right? This has to be a reference. Wait, I did that wrong. If let sum, then down is not a valid down move, which means that we can't do that. You know what we could do? We could match on this, down, left, right, and all of these are going to be board.get. Does mean we're doing extra gets no matter what, but I don't think that matters. What's the, oh, none of these have the references. And then the error is what? Non-exhaustive pattern type, fill match arms. I think the only ones we care about are none, underscore, underscore, valid down move. Then because we will have already matched on the none above, none, valid left move, valid right move. And the only thing we don't cover by that is, so when we go here, we get a match on each of the potential positions we could be in. Because down is first, left is second, and third is right, we get to say if there's no rock or sand in position down, then we can move down. If there's none in left, then we can move left. If there's none in right, we can move right. If there's something everywhere, then we're frozen. And that piece of sand can't move, which means we need a new piece of sand. So in this case, current sand equals this, and we do it again. In the case of a valid down move, that current sand equals left, current sand equals right, and this should infinitely loop forever. So we need to figure out how to break out of this. And I think for us, that is to find the lowest Y position rock. So let lowest rock equals 4.iter. So it's already sorted. Is it sorted in a useful way for us is the question. I don't think so. I think that no matter what will be sorted along the X's. So I think we have to recollect this to actually find the lowest point. Well, we don't have to recollect it. We could scan over it too or something like that, but I'm going to recollect it. Value of type U32, U32 cannot be built from reference to U32. I think that's fine. I think we should just take ownership of this. I mean, we could do references. I think if we into iter, we take ownership and we have to clone it anyway. So maybe we do just take references because the board is going to live until the end of the process. So it doesn't matter anyway. This is going to be rocks vec sort by AB, a.1.comp b.1 rock spec needs to be mutable, and then lowest rock is going to be the last one. Let's debug the lowest rock just to check, and then we go back down, and if current sand dot one is greater than lowest rock dot one, then we break. So we're not doing anything fancy. We're just saying if a piece of sand is below the lowest rock, then it will just infinitely fall. And then we need to return the number of pieces of sand. So we do need to capture the length here. Rock count is going to be board.length. And then here it's going to be board.length minus rock count dot to string. And then we scroll down and find out that are we passing the test? Part 2 is ignored. Let's kill that and run it again. Running 2 tests, part 2 works is ignored. Where's part 1? Oh, it's infinitely running is what's happening. It's not stopping. So the condition that I was looking for infinitely dropping sand doesn't seem to be finishing. Oh, because we set this to that. This is sand plus 1 plus 1 plus 1. So it's always going down. I don't think that we will actually see the output here. So let me do this instead. Let's take the test output and let's shove that into our input.txt so we can cargo run bin part 1. Let's not debug current sand. Let's check out lowest rock first. 5029. So 9 is the lowest rock. And we're going to print line current sand so that we get them all on individual lines. We'll run this and it looks like it's looping. Let's do an additional test. Let's do let I equals 0 here. We'll make it mutable. Well, I equals 1 because we want to count the numbers of sand. And then every time we hit this, I plus equals 1, print line I. And I think we need to get rid of that's 58,018 pieces of sand is too much. Interestingly, we reset every time we hit 508. So what am I doing wrong? If current sand 1 is greater than lowest rock 1, we never hit this, right? Like, get rid of these. That's how many grains of sand we can process, which is a ridiculous amount. We're processing 44,000 grains or 4,400,000, something like that. So we never break. So I'm going to do this and see which one of these we're hitting. Of course, they can't all say down, left, right. It just keeps going down, which feels weird because down is supposed to increase, but it keeps looping at 8. It loops at 8 for some reason. Why does it loop at 8? It's looping at 8 because we get some back for all 3. So I feel like our calculation here has gone awry. So let's check the movement rules. Sand is produced 1 unit at a time, and the next unit of sand is not produced until the previous unit of sand comes to a rest. Unit of sand always falls down 1 step if possible. If the tile immediately below is blocked by rock or sand, the unit of sand attempts to move instead diagonally 1 step down and to the left, which should be +1 for the Y and -1 for X. If that tile is blocked, the unit of sand attempts to instead move diagonally 1 step down and to the right. So +1 on Y and +1 on X. Sand keeps moving as long as it's able to do so at each step trying to move down. I never insert the sand. Oh no. What do we call this? Board? Oh. And this has to be above. Whoops. So we've got an issue with cannot borrow as mutable because we never made board mutable. Really? Yikes. Yikes. Mute board. Just getting rid of all these extraneous logs and stuff. Is it getting moved? Mutable borrow. Okay, so cannot borrow board is mutable because it's also borrowed as immutable. It's immutably borrowed at board.iter.collect, which is board.iter.collect, rockspec sort by, lowest rock, last unwrap, clone. This is going to be a reference, right? So we get away with double dereferencing this, which means that the rockspec can now get dropped. So the issue here was that we had board and we are iterating over board with references to it, collecting that into a vec of references into board, sticking that in rockspec, which we were sorting, and then storing the last value in lowest rock, which was a reference into rockspec, which was a reference into board. So that's why board was sticking around as a shared reference. And then when we went to insert down here, we had a shared reference, so we couldn't take an exclusive reference to do the insert. We fixed that by making the value that we store in lowest rock be an owned value, basically. So we dereferenced it down to the value, which gives us, because they're U32s, basically copies of the U32s. So that looks like the test is passing now. Wonderful. So let's get our actual input, which is all of this. Cargo test that. Cargo vroom 901. Now let's hope that's the right answer. Gold star. You realized you misread the scan. Okay, well, we can cover part 1 first, right? So we do the process for part 1. We already went over the parser, so I won't do that again. We get a B tree set into board. So we just get all of the positions that are filled, basically, is what the B tree set represents. We make that mutable because we're going to insert into it later. We need to get the rock count now because later we're going to have rocks and sand. The rock spec only exists as a convenience function for us to get the lowest rock value, because the way that we are determining whether we are in free fall or whatever is by determining whether we sent a piece of sand past the lowest possible rock that could catch it. I'm sure there's some other way to test that, but this is the way that I came up with that works. So we always start our sand at 500. We use the loop keyword, which infinitely loops in Rust. We break out of the loop by using the break keyword. So we have a condition here. If current sand 1 is greater than lowest rock 1, break. So we could also do a while loop. We immediately set up the 3 possible positions that we could move the sand into, down, left, and right, which are +1 because the Y values increase as they go down. All of them are down 1 on the Y index, and we either go straight down to the left, or down to the right. We can match on the tuple, and we can get each cell in the board. So by doing that, we determine whether there is an empty slot down, left, or right. If there is, then we set the current sand and we move on. This sets the current sand to either the position down, the position left, or the position right. If there is something, we don't need these values here, so I'll just use underscores. If there is something in all 3 spots, then we can't move and the piece of sand is frozen in place. So we insert it into the board and we create a new piece of sand at 500, 0. After we're done with everything, we remove the original rock count from the current board length, so all of the pieces of sand that got inserted into the board, and we get our value. We realize we misread the scan for part 2. There isn't an endless void at the bottom of the scan. There's a floor and you're standing on it. You don't have time to scan the floor, so assume the floor is an infinite horizontal line with a y coordinate equal to 2 plus the highest y coordinate of any point in your scan. I think by their own logic, they mean 2 plus the lowest y coordinate, right? X represents distance to the right and y represents distance down. Or does it mean -2? In the example above, the highest y coordinate of any point is 9. That doesn't make sense though. That's the lowest y coordinate, right? Because the roof is here, which means that this is the floor. This is the lowest rock. We've already calculated the lowest rock. They mean the highest value y coordinate? In any case, the wording here is really weird. In the example above, the highest y coordinate is 9, so the floor is at 11. This is as if your scan contained one extra rock path like -infinity 11, infinity 11. With the added floor, the example now looks like this. Yep. To find somewhere safe to stand, you'll need to simulate falling sand until a unit of sand comes to rest at 500, 0, blocking the source entirely and stopping the flow of sand in the cave. In the example above, the situation finally looks like this after 93 units of sand have come to rest. Using your scan, simulate the falling sand until the source of sand becomes blocked. How many units of sand come to rest? Okay, so we have the lowest point already, lowest rock right here. So I think we can do something cheeky here and do board.get, and if .get is none, then we check to see if it's the floor. And if it's the floor, so each of these, so some can match first, right? Because it only matches if they're all sum. I think I'm gonna do that. So let's go check option in the docs. And I don't really want map. I want something like map error. Returns the option if it contains a value, otherwise calls f and returns the result. That sounds like what we want. Returns sum if exactly one of self. OPTB is sum, otherwise returns none. I think we need a function. So or else we return or else. So when we do this, we do board.get down. It either has a piece of sand or a rock in it. If it doesn't have a piece of sand or a rock in it, then we do or else. If down.1 is equal to lowest rock.1, which means that it is going to hit the floor on the next iteration, then we do sum lowest rock, otherwise we do none. And we do the same thing here for all 3 of them. And I added extra commas, that's why it flashed red just then. This is going to be right.1. It doesn't matter what lowest rock is, because if we return sum here, then we just return current sand. So lowest rock is just a hold in or a stand in for this. So let's see, what's the answer? How many units of sand come to rest? It's the same question. What is the answer for, this is the other thing we need to do too. If a unit of sand comes to rest at 500 0 is our new condition, 93 unit. The answer is 93 for part 2. We start doing the test. We can watch the test, which should run and fail. It does. And then I just modified process part 1, didn't I? Whoops. Okay. So let me copy and paste this into part 2 because this is the answer for part 2. And then let me take the code that I just added to part 1 off because that was silly. So part 1 is succeeding and part 2 is going infinitely right now, I think, because our test condition needs to be what? If current sand is 500 0 until a unit of sand comes to rest at 500 0. So we get rid of this up here and we wait until a piece of sand comes to rest. Oh, this is actually easier than I thought. So we leave this up here. So we can switch from loop to while let, which will be fun. While let none equals board.get 500 0. And we need to reference that for it to count. We are not getting the right answer, unfortunately. 69 and 93. So that means that this logic is wrong in some way because it doesn't, I think it works, right? I wish it was easy to print this out to look to see what was happening. So none happens a whole bunch, which is exactly what we want. Oh, you know what I did though? This needs to be +2 and then the tests pass. So I forgot to +2 on the lowest rock. So we've modified our example to use while let, which is very cool. So this loop will run while board.get returns none, and it'll just keep doing that every round. And then we fixed our logic by doing board.get on each of the potential positions. And if those potential positions are empty, we check to see if the potential position is going to be in the imaginary floor that we don't have in the board. And if it is, then we return the imaginary floor. Otherwise, we return none. And the imaginary floor value doesn't matter. It just matters that we return some here. So if I was going to productionize this code, I would probably actually have a value here that wasn't some, just to make it clear that there's a lowest floor. So let's see if it works. Run part 2. It takes a little bit to run. Okay, it does finish though. So can we time that? Is that easy? So we get like 11 seconds on that runtime. Let's be clear that that is running with debug. And if we run it with release, it takes 1/3 of a second. So let that be a lesson. Because in debug mode, this program takes 11 seconds. And with the release flag, this program takes 1/3 of a second. So there are real strong optimizations that happen when you use that release flag. And yes, that's 1 gold star. Huzzah. And we get our nice little ASCII art. The little waterfall popped up here. So I don't think that the day is particularly interesting in terms of criterion. There's 2 testing tools that I want to use. DAT, D-H-A-T, and Criterion. Criterion is for runtime speed, and DAT is for heap memory profiling. But looking at our program, we really don't do very much. We keep current sand around. We generate an extra 3 tuples, and then board grows by that tuple. So board will be the domination of because it'll just keep adding another one. And we don't really keep much else around. And then our parser doesn't really do that much either. Our runtime is still pretty low. It's still 1/3 of a second. I think that because this algorithm has to happen sequentially, that we're not going to get a ton of speed up. There's nothing we can do that's pretty trivial, like Rayon would let us do like par iter, but I don't think that actually is useful. But probably the only time that's useful is in the parsing, but generating a bunch of values doesn't sound like a very intense process either. What's this recording? It's not bad. All right, well, I think I'm going to cut it off there and we'll pick another day for Criterion and DAT. So I hope you enjoyed the video. Have a great rest of your day and let me know how y'all solved this in the comments. Let me know if there's anything I could have done better or if you have any questions about anything. I know we returned iterators from the parser today. That is a new thing for, I assume, most of you. So let me know if you have any questions and I'll see you tomorrow.